Operationally, a firm functions as a bounded mathematical space, a topographical environment where raw physical inputs are converted into a maximum possible yield. We map this physical reality using a production function, y equals f of x1 and x2. The inputs, like capital and labor, sit here on the horizontal floor. The output, y, is mapped on the vertical axis. Together, they form a curved three-dimensional production surface. If we lock the output to a constant value by slicing this surface horizontally, we capture every possible combination of inputs that achieves that exact same yield. When we map these intersections onto the floor, we create isolated two-dimensional curves called isoquants. This resulting geometric topology contains every possible operational state of the firm. It maps the physical constraints of production before costs, prices, or market factors enter the equation. This graph illustrates the axiom of monotonicity, or free disposal. Notice that the curve tracking output, f of L, never turns downward. Injecting excess input into a system will never decrease the total output, because a firm can simply discard the excess without penalty. On our three-dimensional production surface, this means moving strictly outward along either the capital or labor axis will never result in a drop in altitude. The second structural rule is convexity. This dictates that mixed production techniques, averaging capital and labor, are always at least as efficient as relying heavily on a single extreme input. We can prove this geometrically. This chart shows two extreme points on the production frontier. If we draw a chord between them and find their linear combination, the midpoint, it sits strictly within the feasible production set, representing a highly efficient mix of both methods. Monotonicity and convexity act as mathematical guardrails. They force the firm's topographical model to remain smooth and predictable, allowing us to deploy calculus to measure its internal dynamics. To analyze this system, we use three distinct metric pillars. The first is Grenz's product, or marginal product. This measures how output reacts when we alter one specific input while strictly freezing all others. Mathematically, freezing the x2 axis cuts a rigid vertical slice through our 3D surface, revealing a 2D curve. Tracking its slope reveals diminishing marginal product. Moving further along the x1 axis, the slope flattens. Each added input yields less output. This mathematical reality is driven by physical constraints. If you assign a continuous stream of agricultural workers to a strictly fixed plot of land, the physical space quickly becomes crowded. Eventually, a new worker adds virtually no new crop to the harvest. Remember, Grenz's product is strictly a local measurement. It measures the inefficiency creeping into a single dimension of the firm, while the rest of the operational system remains completely frozen. The second pillar, the technical rate of substitution, removes the fixed constraints. It measures the challenge of swapping inputs against each other without altering the final output yield. To visualize this, we shift our perspective from the vertical slice down to the horizontal isoquant contour, mapped cleanly on the x1 and x2 axes. This equation defines the exact ratio of substitution. It calculates exactly how much of input 2 must be added to perfectly offset a measured loss in input 1. It is directly equivalent to the negative ratio of their marginal products. As a firm relies too heavily on a single input, the technical rate of substitution diminishes. Sliding along the curve, the proportions shift. Giving up 1 unit of capital eventually requires a massive injection of labor just to maintain the exact same production volume. This horizontal contour defines the firm's operational agility. It proves mathematically how easily or painfully a firm can pivot between capital and labor during an economic disruption. Local constraints govern daily operations, but the third pillar, Scalanerträge, or returns to scale, measures the global expansion of the entire input space simultaneously. This diagram maps a simple production possibility set with 1 input and 1 output. From this baseline, we need to determine if the maximal possible output will scale proportionally when we increase the inputs. We test this homogeneity by multiplying all inputs by a constant factor, t. If we double the capital and double the labor simultaneously, we map exactly how the total output reacts. Scaling the coordinates globally triggers 3 possible geometric outcomes on our surface. The output can rise at a perfect proportional ratio for constant returns, slope exponentially upward for increasing returns, or flatten out for decreasing returns. The physical standard for constant returns to scale is the copy exactly principle. A server farm doubling its processing power does not reinvent its architecture. It simply duplicates the exact operational layout of its motherboards and cooling systems to yield exactly double the output. While marginal product manages the granular daily tweaks to the system, returns to scale dictates the physical limits of how large the firm can grow. Precision in microeconomic analysis requires distinguishing between the local behavior of a function and its global geometric properties. The Cobb-Douglas production surface demonstrates how these two dimensions interact. A firm can experience diminishing marginal returns on every individual input while simultaneously maintaining constant returns to scale across the entire system. If you isolate a single variable on the left, the vertical slice flattens out. That is the local limit of adding labor to a fixed factory. But on the right, if you expand the factory and labor force simultaneously, the production volume rises linearly. Operationally, the firm is a topological space. You use marginal product to navigate the vertical axes, the technical rate of substitution to traverse the horizontal contours, and returns to scale to measure the expansion of the entire environment. Mapping this axiomatic bedrock provides the coordinates for everything that follows. Without defining these physical boundaries, the logic of cost minimization and profit maximization lacks a mathematical foundation.